Hi, my name is Sarah Hausman, and I'm going to be talking to you today about the topology of the alphabet and how it can be used to bring higher level mathematics into the elementary school classroom. First thing we need to do is start by defining topology. Topology is a branch of mathematics that studies properties of objects that are preserved through twisting, stretching, and other deformations. All this means is that topologists study things that stay the same when they are stretched or smushed, but not torn or broken. Now, this might sound like a very narrow and boring field of mathematics, but there are actually all kinds of cool things that you can do with topology. Topologists like to look at unique objects and analyze them, and one of those objects is called a fractal. This is a computer-generated fractal, and all a fractal is a never-ending pattern. So you can see that the smaller portions of this fractal resemble its larger portions. Here is a real-life example of a fractal called a Romanesco broccoli. You can get this at the farmer's market, and you can see that its smaller spiraling cones resemble its larger spiraling cones, an infinite pattern, so it too is a fractal. You can also look at the Mobius strip, which is an object with only one side that was invented for use in conveyor belts. And this is called a Klein bottle, which is kind of like a three-dimensional Mobius strip. It's also one-sided, so to speak, so its inside is the same as its outside. Those are all examples of very cool and unique topological objects, but you can also analyze ordinary things using topology, and that's what we're going to do today. We are going to use topology to examine something that all of our students are hopefully familiar with, the alphabet. The first thing you're going to need is some Play-Doh. Here is my favorite Play-Doh recipe. It's a lot smoother and easier to handle than normal store-bought Play-Doh, and the Kool-Aid keeps it from having that gross Play-Doh-y smell. Now, I know that some of you upper grade teachers are going to think, oh, my kids can do this activity without the Play-Doh, and that's probably true, but I suggest that you break out the Play-Doh even with your upper graders. I think a lot of students and adults believe that manipulatives are childish, and once you reach a certain grade, you don't need to use them. But I believe that they are actually extremely helpful for older students too. So I like to involve manipulatives, like this Play-Doh, in lessons that involve complex mathematical concepts to try to remove some of that stigma. And I don't care what they say, everybody's going to get excited about Play-Doh. So I've split this lesson into two activities, one that is more appropriate for younger students and one that is more complex and appropriate for more advanced students. The first lesson, the simpler one, draws on a topological equivalence called homotopy. Now, what is homotopy? If you want the official math definition, there it is, but that has a lot of scary words and symbols in it. So for our purposes, the question that we need to worry about is how many holes does it have? Two objects are homotopic if they have the same number of holes. So this rectangle and circle are homotopic because they both have 0 holes. The number of holes is the only thing we're concerned with here. So even though one is a rectangle and one is a circle, or one has corners and one doesn't, or one has straight edges and one doesn't, we don't care. Since they both have 0 holes, one could be stretched and or deformed to make the other, so they are topologically the same. However, if we look at the sphere and the torus, which is the math word for a donut, these do not have the same number of holes. Even though they are both three-dimensional objects, the sphere has 0 holes and the torus has 1 hole, so one cannot be stretched and or deformed into the other without tearing or breaking. So the sphere and the torus are not homotopic. As you can see, counting the number of holes is something that's relatively easy and definitely something that our younger students can handle. So now we are going to turn our attention back to the alphabet. Since your class will be analyzing how many holes each letter has in the next activity, it's important to choose whether this will be done with uppercase or lowercase letters. As you can see from the letter B, the number of holes is often dependent on the case of the letter, so as the teacher, you need to choose the case that your students will be analyzing. For this example, I have chosen to look at the capital letters. To begin this activity, each child should be assigned a letter and given a printout of that letter. For this example, I will be working with the letter A. The first thing students need to do is color their letters. As the teacher, you can just let your students color their letters however they want, or you can impose additional coloring requirements. You could require students to color their letters using patterned stripes to bring in some extra math concepts. You could tell them that if they have a vowel, they have to color it one color, and if they have a consonant, they have to color it another color to bring in some ELA. Coloring requirements are a really good way to sneak in some other subjects into this lesson. After your students color their letters, they need to cut them out. And you will notice that I have cut out both the perimeter and the whole of this A. You can have your students cut out only the perimeter if you want, since that's easier for smaller hands. But since we're looking at the number of holes each letter has, I like to help them cut out the holes as well to make that concept a little more obvious. Next, you need to break out the Play-Doh. Your students should make their letters out of Play-Doh, placing their new Play-Doh letter on top of their paper letter. Especially for your kinders and your first graders who are still struggling with writing and identifying their letters, this is going to be a really helpful step. After students have made their letters out of Play-Doh, they need to determine how many holes their letters have. And I can tell by looking at my A that it has one hole. Once everyone has determined how many holes their letters have, you should compile this information as a class, and there are a lot of different ways to do this. You can do it verbally, you can make a class list, but my favorite method is making a class table or graph. This one is meant to be a cheat sheet for you. I have sorted the letters into their homotopic equivalence classes, which just means that I've sorted the letters so they're grouped in with the other letters that they are homotopic to. So the letter C is in the 0 holes equivalence class with all the other letters that have 0 holes. With your class, though, I recommend drawing this table on the whiteboard and then asking students to come up one at a time and tape their colored paper letters on the board in the correct row. This way you can stress alphabetical order by asking things like which letter comes next. And then you can involve students in interpreting the graph when it is complete. So you can ask questions like which row has the most letters, which row has the least letters, and how many more letters are in the 1 whole row than in the 2 whole row. You can also do this activity again with lowercase letters and then have your students compare the uppercase and lowercase graphs. That concludes the first activity in this lesson. Now we're going to turn our attention to a more complex type of topological equivalence called homeomorphy. Again, there is the big, scary official math definition if you want it, but for our purposes, homeomorphy comes down to 3 questions. How many holes does it have? How many 3 vertices does it have? And how many 4 vertices does it have? Now, what are 3 vertices and 4 vertices? A 3 vertex is a point at which 3 lines meet. Similarly, a 4 vertex is a point at which 4 lines meet. Here are some examples of 3 vertices and 4 vertices, but there are actually infinite examples that you could come up with. And at this point, it's important to recognize that I could bend the first 3 vertex example into the other 2 examples, and vice versa. And the same applies to all of the 4 vertices. Now this brings us to 2 vertices. Why don't we care about 2 vertices? If we take the 2 vertex on the left, I could theoretically bend it into the 2 vertex example in the middle. But I could also bend it enough to straighten it out, and then I could just leave it alone. And suddenly my 2 vertex is just a straight line. So since a 2 vertex can be bent into a straight line, a 2 vertex and a straight line are topologically the same. And that's why we're only concerned with 3 vertices and 4 vertices in this activity. Now, because we're looking at 3 vertices and 4 vertices, it's important to pay attention to the font that you're choosing for your students or the way that your students usually write their letters. If we consider the letter J, the J on the left has 0 holes, 1 3 vertex, which is circled in red, and 0 4 vertices. The J on the right has 0 holes, 0 3 vertices, and 0 4 vertices. So if you're doing this as a class activity, make sure you settle on how you're going to write certain letters so everyone is analyzing the same thing. I have chosen to use this set of letters, which is most similar to the way that my students have been taught to form their letters, but you can choose any font you like as long as it is agreed upon before the lesson. So now back to our homeomorphy activity. I like to begin this lesson by choosing a letter for myself. I have chosen my very favorite letter S. I then assign each of my students another letter and have them sort the rest of the letters into the categories homeomorphic to S and not homeomorphic to S. In order to determine if a letter is homeomorphic to S or not, you have to break out the Play-Doh again. Students should begin by making the letter S out of Play-Doh and determining how many holes, 3 vertices, and 4 vertices it has, which in this case is 0, 0, and 0. S is a pretty easy letter. Then they have to morph the letter S into their assigned letter, but the rules are They can bend, stretch, and smush the letter, but they can't change the number of holes, 3 vertices, or 4 vertices. So no tearing or breaking. Let's say I have the letter T. I now have to mess with my Play-Doh S to see if I can make it into a T without changing the number of holes, 3 vertices, or 4 vertices. Here's my first attempt, but it doesn't quite look like a T. Here is my second attempt to make my S into a T, but that didn't quite work either. So now at this point, I'm pretty sure I can't make an S into a T without changing the number of holes, 3 vertices, and 4 vertices. So T is not homeomorphic to S. Now, I could have skipped all of these attempts by simply looking at how many holes, 3 vertices, and 4 vertices T has, and realizing that even though S and T both have 0 holes and 0 4 vertices, S has 0 3 vertices, but T has 1 3 vertex, so there's no way that S could be transformed into T. But this is a shortcut that you want to let your students discover on their own through this activity. Once everyone has determined if their letters are homeomorphic to S, you can create a class table like this one. Even though your students didn't have paper letters this time around, you can proceed in the same manner, asking each student one by one where their letter should go and having them write it up on the board in the correct column. And yes, it should be noted that S is homeomorphic to itself. For part 2 of this activity, you can assign each student a letter and then have them split the letters into equivalency classes like we did during the first activity. The difference here is that while in the first activity we categorized letters by how many holes they had, now we have to take into account how many holes, how many 3 vertices, and how many 4 vertices they have. So let's say I've been assigned the letter Q. Here is my letter Q. First thing I'm going to do is make it out of Play-Doh. Next, I need to look at my Play-Doh letter and determine how many holes it has. As you can see from the blue circle, Q has 1 hole. Next, I need to determine how many 3 vertices and 4 vertices Q has. I've circled Q's only vertex in red, and you can see that 4 different lines meet there, so it's a 4 vertex. So the letter Q has 0 3 vertices and 1 4 vertex. Just as in the first activity, you can collect all of the class's information in a variety of ways. I have chosen to display the information here in a table, which can be compiled on the whiteboard. And you can ask your students to answer a variety of questions about the completed table, such as which equivalence class or category has the most letters. You can ask students questions about specific categories or letters, such as which letters are homeomorphic to E. And since you're doing this activity with slightly older students, you could also have them run some type of statistical analysis, such as finding measures of central tendency on the class's final data. That brings us to the end of this presentation. I have listed some references and additional resources here if you would like more information about any of the concepts that I have discussed. So definitely check those out, and I hope that I've inspired you to integrate some higher level mathematics concepts into your elementary school classrooms.